this computer. All right, here we go. Welcome everyone to our first official class lecture. Hope everybody's getting oriented to the program. I just want to do a couple of, quick announcements. If you did not see the recording from last Thursday, please do watch it. I think there's valuable information. Probably most of your questions in terms of how you get a grade and how you get through the course is going to be answered in that. Just as a reminder, first lab is going to be due Sunday. So hopefully you started that. And when you do the labs, if I didn't say this on Thursday, so if you do that start lab, it's going to open an RMD file. You can just put your answers in that document. So any place you need to put an answer, and mostly at the bottom, there's sort of an on your own section. And we tried to put in there, insert your answer here. If you need to write R code, great, you can do that. If you just need to, sometimes it's going to ask you to describe something, you can do that. You can just type kind of mix back and forth. So just put it in there. I think that'll be better for you going down the line, because then you can look at it, review, and you can kind of see everything together instead of creating a separate document. The other thing I want to point out is, I hope this link still works. As you're learning R and all that kind of stuff, RStudio, or I guess it's Posit now, has a whole lot of cheat sheets. So let me see here. There's so if you're getting familiar with the IDE, there's an IDE cheat sheet. If you have to work with dates, which you don't have to really a lot in this class, that's really great for that. There's a ggplot2 cheat sheet. We'll talk about ggplot2 not tonight, but soon. dplyr, you might have actually already started encountering that 607. That's for like a lot of data transformation. Anyways, these are all like 2-page cheat sheets. I think they're really fantastic, great little references if you just have them handy. So I just want to summarize. So thank you everyone who completed the sort of the formative assessments. I think this is great. Looking at to see where you folks are starting. A lot of experience with descriptive stats, a little bit with regression, null hypothesis testing. So this is kind of where we expect you to be. So even if you kind of have some, hopefully, but in the next 15 weeks, you're going to be experts in all of this except for SPSS, I think. That's a holdover for when I teach in other programs. I kind of don't expect people to have experienced that, and you're not going to get any in this class, so don't worry about it. And then in terms of like math anxiety, I love this. I need to contrast this to like I think I might have mentioned I've taught statistics in a lot of different contexts, including in a criminal justice department. I've obviously taught in educational departments. And the variability or the difference in these results from like this program versus other ones, it makes me so happy that all of you, well, except 2%, which is probably one person who is neutral on whether or not they think they're going to use math in their future. Okay, if you're in data science, you're going to use math in your future. So if you're unsure about that, and Arthur and I have I jabbed them in our orientation. I have the opinion that data science is just rebranded statistics. Arthur disagrees a little bit. We can have a fun debate about that at some other point. I'm so glad most of you find it interesting. And then things where it's kind of on the other side. I'm glad it doesn't make most of you feel nervous. If you do feel nervous, Angela and I are here. Like if you're doing the self-regulated learning assessment DAX, which is something we're asking you to do, and really look at those resources, I think there's a lot of skills that I think that we want you to kind of develop that make you successful students. One of them is understanding, appreciating, and addressing anxieties. So we did this math anxiety in DAX. We looked at mostly test anxiety. Help seeking is another one, right? If you're good at help seeking and reaching out to us, that goes a long way to being successful. Angela, do you want to add anything else to this? Or?
No, just echoing Jason to say that reach out. Help seeking is one of the self-regulated learning approaches. If you guys have taken the DAX, so reach out sooner than later, right?
No.
We still want to hear from you at the end of the semester, but by the end of the semester, when you say, "Oh, I've been so lost for so long," we would get upset because you should be coming to us sooner. Okay, so
And thank you for your note in the chat. And we'll talk about Likert visualizations when we get to data visualization either next week or the week after. I'll show you how you can create these plots. I have a strong opinions on how you should analyze Likert response data, and so I'll be short. Tonight's class is going to largely be about like where data comes from, how we get data, and what does data represent, really. And so to start, we want to start right up front and talk about this notion of validity and reliability. Because in data science, one of the things that you'll probably do a lot is you're going to try to predict outcomes using a variety of, models or statistical methods or, whatever it might be. And a lot of times if you, talk about predictive modeling, we're kind of concerned with the accuracy of the prediction and all this kind of other stuff. But I don't know in data science if we pay enough attention to the measures that go into that. And in particular, whether or not those measures are valid for what we think they measure and whether or not they're reliable. I can tell you how many models I see that it's sort of almost black box. And sometimes they are black box, like neural networks, for example. We're not entirely sure what happens inside. Like we throw this data in and it, processes the data and we get some predictions on the other side. And, that's, fine and that's great in solving some models, but a lot of times we want to make sure that what we're measuring and what those measures are in terms of relating on what we want to predict are both valid and reliable. So this chart here is trying to show the difference. First thing we need to say is like reliability is necessary but insufficient for validity. So Angela and I do a lot of work where we are concerned with the validity, and so we look at reliability measures. But that's part of it. But that doesn't necessarily mean you have valid. And so when we say something is valid, means it's measuring what we think or say it is measuring. Okay. So right now, Angela and I are kind of a big part of our research is about college readiness. And so we're doing a lot of work, and our work is kind of related to this area with SAT and ACT, which a lot of you probably are aware of. Maybe it's something you took in high school that you needed to do in order to get college. And it's been used by colleges for decades as a way of deciding who should get into colleges or which colleges, have different thresholds for admittance. It turns out right now there is a lot of question about the validity of that assessment in terms of what it says it's measuring, right? In particular, because we're, now really coming to terms with the biases that are in it, right? Those from higher social economic status tend to do better than those. So it's not really just academic performance or knowledge or IQ or whatever you want, intelligence, right? It's, there's all these other kind of covariates that kind of really question the validity, right? So sometimes we take this for granted. In the data science world, we use, different measures, and we'll show examples later in the course, right? You have things like Facebook, where they could say through likes and what have you, they can predict sexual orientation or other things. And it's like, well, are likes really a valid measure of one's personality? All right. Or, Myers-Briggs is another popular one, right? I think there's a lot of questions of validity. Is that really, a valid measure of this thing? And is that thing really a thing, right? So these things we need to think about. So here, right, so we can have non-reliable. So if we think of, we're trying to get to the bullseye, right? That's what we're trying to measure. Well, we can just have plain non-reliable. We throw the darts, they're all over the place, right? But we can have reliable measures that are not valid, right? And that's what this is trying to show, right? And we'll look at measures of that, and sometimes we'll do that and we'll say, okay, we have a reliable measure, but it's not measuring what we think it's measuring, right? It's way off the target. And so ideally what we want is things that are reliable, meaning there's consistency in the scoring and they're actually hitting the target that we want to hit. Okay, so in order for an assessment to be valid or a measurement, we need it to be reliable and valid. Now, in terms of validity, this tends to be an ongoing process, and there tends to be sort of these 5 pillars or forms of evidence for validity. And Angela probably you want to take a stab at this slide? I added it just like 2 hours ago and I'm throwing her on the spot, but she's sort of, I think, the measurement expert more than I am.
Sure. So validity evidence, there are two approaches that we can think about, use as we think about validity evidence. And the one that was the older version or more traditional version is called the Trinitarian approach, and they focus on content, criterion, and construct validity, right? But then for the more recently, we have come to conform to something called the unitary approach to validity, and that's cited in the or written about in the AERA standard
AP,
book.
NCME.
That's
Yeah,
yeah,
right.
that's been our Bible because we look at it, we review it as just what is it exactly that we the sources of evidence that we want. And so there are 5 sources of evidence that we can collect, all of them under this idea of construct validity, which is are our measures really measuring the construct as in the idea or the topic or the um what is it, like anxiety is an example of a construct, right? And self-esteem is another, self-efficacy, motivation, those are all examples of constructs. And so are our measuring or are our measures appropriately and accurately measuring those? And so there are 5 sources of evidence. Content is essentially very briefly is a are the is the content within that measure appropriately covering the coverage? Is it covering that construct appropriately, right? And then response processes is about, are the participants or our target audience interpreting and responding to those items the way that we intend, right? If they don't, then that measure or those items are not really measuring gathering information that we intend. And so that would not be valid. And then internal structure has to do with running CFA and EFA. So that's confirmatory factor analysis and was it exploratory factor analysis, which gets at how well do those items hang together, right? And so, and then relations to other variables have to do with concurrent validity, predictive validity. So essentially, is our measure highly correlated with variables and constructs that should be highly correlated and less correlated with variables that shouldn't be correlated. And so an example that I would use is anxiety it could be highly correlated, moderately correlated with depression, but highly correlated to another measure of anxiety, right? And it would be probably not very correlated with enjoyment in math because those constructs are not really connected, for example, right? And then consequential validity has to do with fairness and biases and all of that, and the purposes versus the use of the instrument or the measure that we designed. Is it being used in for the intended purpose? And so if it is not, and if it's used maliciously, then that's not good, right? And there are intended and unintended consequences, which is our job to sort of monitor and alleviate if there are unintended consequences.
Great. Thanks, Angela. That was great. Um, so let's look at we'll go through a case study here. So, we want to develop a study, right, that treats chronic fatigue syndrome, just by way of example. And so we have sort of this approach, right? We can use cognitive behavior therapy as one approach to potentially helping chronic fatigue syndrome, right? And so in this study, we recruit 100 or 142 patients are recruited through referrals to primary physicians. So we, say we're going to reach out to our, local primary care physicians and say, we're trying to do this study. We want to recruit people who have chronic fatigue syndrome to test this thing. So that's what we try to recruit. But then we only end up getting 60 of the 142 patients actually entered the study because some were excluded because they didn't meet the criteria, had bad health issues, or just refused to participate in the study. So this is actually a real study. There's citation is there if you want to look at it, but it's an exemplar of like some of the challenges we're going to have about our data and what our data tells us about something more broadly, right? So we can collect data on these 60 patients, do a intervention on some or not, and right, and that could say something. But we want, what do we want to say? Like, what is our conclusion? We would like to say something about whether or not cognitive behavior therapy is effective for people who have chronic fatigue syndrome. But because of the way the data is collected, right? So we have a sample, and that hopefully that sample informs something about some population, larger population, right? And then we also oftentimes want to make inferences about whether or not something causes something else. So we're kind of trying to make inferences in two ways. One, in terms of whether or not there's a cause and effect, and sometimes whether or not this is generalizable to some larger population. And, ideally, we often want, we want to say both, but in reality, sometimes we can only do one or the other. So right away, I'm looking at this study, and the fact that we had fewer than half actually participate in the study brings up like issues of bias, right? And so those are things we're going to have to look at in terms of of and how we can make our conclusions and inferences. So in this particular study, we're actually going to do a randomized control trial. So for the 60 people who agreed to participate or that actually are successfully in the study, we can say take half of them and give them the cognitive behavior therapy, and the other half we can give them some other condition or control group, we often call them. In this case, we're just saying, we're just going to give them exercise and relaxation. That's something that's different than what we're interested in, right? We're really interested in if this is effective. And so we kind of want to compare that to the status quo. Okay. So the results of this study, right? So we show here for those in the treatment, we did a 6-month follow-up, measured to see if there was an improvement in their chronic fatigue syndrome, and 19 of the 27 in the treatment group had improvement, where only 5 of the 26 in the control group did, right? So it's a 70% versus a 19%. So on the surface, right, we might say this cognitive behavior therapy is beneficial in terms of improving chronic fatigue syndrome. Now, we're going to spend the next few weeks defining, right? So this is just saying on the surface, there's an effect. We'll define statistical methods to quantify how certain we are that there is truly an effect, or whether this difference could be because of some random chance, right? That's a lot of what we're going to do. But in terms of making those interpretations on those statistical tests, going to rely on the study design, right? And so the key in this example is that us as researchers randomized people between those two. So when we think about causality, the key is the control, and that the difference between the two is because of that. Okay, so understanding the results. So classic, and we're going to look at, simulating coin tosses a lot, at least in the first couple of weeks. If I, say I'm going to flip a coin 100 times, right, I sort of expect to get roughly 50 heads and 50 tails. But if I got 52 heads and 48 tails, would you immediately conclude that there's something wrong with the coin? Or would you say, that's reasonable, right? That's close enough. What if I had 60 heads and 40 tails? What if I had 70 heads and 30 tails, right? Somewhere in that spectrum, we're going to be like, I suspect there might be something wrong with the coin, and the coin might not be fair, right? And so a lot of, we're going to quantify that. Like, how far away from that expected value do we need to get before we say, I'm pretty certain, and we're going to quantify that uncertainty, that something is wrong with the coin. Okay. So in this case, right, in this study, we had 51% difference. That's probably real. How real we'll define as we go along. Okay. So then the next piece, right? That's great. So here I'm just going to stipulate, without going through the actual statistical procedures, that there is a real effect. So we can say, at least for these 60 people, cognitive behavioral therapy was effective. Now, the next question we want to ask, is that true for all patients with chronic fatigue syndrome? And so are the characteristics of our sample representative of the large one? And in this data set, we actually don't know. I can't actually answer this question, because if all 142 who were recruited or identified participated, I'd probably feel better. The fact that we had fewer than half participate, means we need to do a little bit more checking. And types of things we're going to do is we're going to look at demographics, right? Between all 142, or all people with chronic fatigue syndrome, if we can have a census, perhaps, and we can compare it and say, okay, we have roughly the same number of males. The sex breakdown matches up, ethnicity breakdowns, social economic status, what have you. Any variables that we think might be related to, or give reasons to why somebody would choose or not actually end up in this study. And we're looking for that balance, right? We want it to be representative, right? So that's that generalizability piece. We're not saying anything about causality, just simply that the results that we see from the sample represent that population writ large that we're more interested in. Okay. So the reason why we are so concerned about this is, in general, we are working with samples, which is a subset of some population. So, populations can be pretty small. So we have, I don't know, 200 students in the MSDS program, and we want to get an opinion on the programming. And so we might send a survey out to, 20 of you, if we randomly select them and 20 of you answer this survey, because it was randomly selected, we're going to assume that those responses of those 20 are sort of representative of the 200. Okay. So that would be a sample. Now, alternatively, we could ask everyone in the program, right? And then we could do a census. And as long as the vast majority, respond, that's good. Now, when you're doing a census, we're going to see there's some kind of sort of different rules. But I know for the Department of Education, when they do national studies and they do sampling, or if they're doing census, they need 85+% participation in order to kind of say it's a valid census. Anything less than that increases a significant threat of bias. Okay. Now, if you're doing sampling, it turns out we need to sample less than 10%. And if you get to more than 10%, there's sort of this dangerous area where you're bigger than a sample, but not a census, and then the inferences become really hard. And I have some simulations that we're going to show later on as to like why 10%. It turns out there's sort of just to kind of tease it, right? There's this, when you get more than 10% sampling, you're actually introducing violations to independence assumptions. Like, when we're doing this, we're assuming one person's response is independent of another person's response. And we're going to see that assumption come up over and over again. Good. So censuses are often very, very difficult to do. There are some situations, like I did educational research now for a couple of decades. And a lot of times we actually have census data for MSDS students. Like we know everybody who's in the program, we know where you are in the program, and we know basic demographics about everybody in the program, right? So that's great. But we have only samples of responses in other criteria in terms of like satisfaction, mostly because we ask everybody to complete like course evaluations, but usually we get, far less than half of you who will complete it, right? So then that becomes a sample. So those are kind of two things. In the United States, we actually do a census every 10 years. It's actually in the Constitution that we do it. So the last one was done in 2020. You may remember it's sort of a giant effort. As data science, you should be aware that data is readily available. There are packages to get that in if you're interested in some of the things. And there's actually a supplement. They used to do something called the long form. So they did a census, and then they did a sample of people in the census to ask more questions. They now changed the design, so that's sort of an ongoing rolling process. And that's called the American Community Survey. And if you want to look at 5-year averages, and I think you can get down to census tract, that data is really valuable and it's publicly available. If you want something a little bit more finer grain, there are ways to get like restricted use data. But if you look up the American Community Survey, cool data set, freely available, lots of interesting things you can do. A great data set to potentially do a data project on. So when we do sampling, there are different biases that can kind of occur. So first is non-response, right? And this is actually becoming an increasingly big problem in the polling and political polling world. That pollsters are constantly trying to get voters' attitudes or in terms of policies and in terms of who they're going to vote. But the non-response rate is so high that it is really bringing into question the quality of the poll results. And this is becoming a bigger and bigger problem over the sort of the last decade or so. So non-response is a real issue. Voluntary response kind of flips it, right? So that's an issue we see and something I'm actually in our faculty meetings discuss a lot. Like, so we do end of course evaluations. You will also all at the end of the course, all be asked to complete a survey on the quality of this course. And like I said, in best case scenario, we've been getting like 30 to 40% of you will actually respond. As an aside, as sort of, again, begging you early, like we actually read those comments and they matter to us. We make improvements in the course based on feedback. So Angela and I take them seriously. So do respond when that time comes. But usually the people, what I find, the students who respond are the ones that either did really well in this class or really poorly. And those are the ones who volunteer. And so there's a sort of a bias, I think, in the response there. So that could be an issue. The other is convenience sampling. And this has been a major criticism of like psychological research now as we go through. There's, I say this, it's the weird acronym, white, European descent. What's I can't remember. Weird research. What is yeah, so the acronym of weird, what does it stand for? Western, educated, industrialized, rich, and democratic, right? So if you took psych as an undergrad, right, a lot of these studies are things that we think we know, or if you read about Freud or whomever, right? So Freud made all these conclusions about development, and his conclusions are largely based upon married Italian women in the mid last century, right? Because it was a convenience sample. That's who was around him, and that's who he talked to, and he developed these theories based upon those. But the weird is like, kind of get this. This is a also a big issue in data science, because a few years ago, when Google first turned on their image classification system, they started identifying African Americans as apes, or vice versa. If you typed in apes, you would get pictures of African Americans, or vice versa, right? And part of the reason that came about is that they used a convenience sample. They used pictures of people around them. And if you look at who's employed at Google and in Silicon Valley, is a lot of like white males, right? And so that they used a convenience sample to train their models. So this is an issue kind of across the board. So how do we do random sampling? There's a lot of different approaches, and depending on what you want to do and kind of inferences, obviously the easiest is just a simple random sample. So if we have this picture here that depicts our population, we have all these blue dots. I'm just going to take a random number generator and I'm going to sample or measure these red dots. Pretty basic. But sometimes we're going to care about a particular variable, right? So ethnicity is a classic, right? I want to ensure in my sample that ethnicity is representative of the population. So if I kind of know in the population, I could stratify. And so you can imagine any of these variables. So I'm going to stratify my data so that, each stratum has a similar characteristic. And then within each strata, I will do a random sample, right? This is great because now I ensure my sample is representative of the population at large with regard to whatever my stratifying variable is. Now, there's another approach where sometimes collecting, a lot of times collecting data is really expensive. The one example I think of here is like the Department of Ed every 2 years collects data on high schools, or actually grades 4 and 8 students across America. It's part of the National Assessment of Educational Progress, sometimes called the nation's report card. In fact, I think it's starting to hit the news because I think the latest results are coming out, and a lot of the articles I'm seeing are based on this data. Like we're seeing a small bounce back from sort of a COVID dip. Okay. But the way they do it, because it's meant to be nationally represented, it becomes really challenging and cost prohibitive to actually do a simple random sample. Because if I randomly sample a school in a suburb of Ohio and then one in Nebraska and blah, 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 all over. So what they've done is clustered or created regions in the United States, a whole bunch. They're called clusters. And so they first randomly select the clusters that they want to go, which are geographic regions. And so every 2 years, they pick a different bunch of clusters. And so, okay, now within that cluster, we'll randomly select some schools so that the travel time and the logistics of collecting data changes. Now, there's a little bit more complication because there are actually certain clusters that are always sampled, like New York City, LA, Louisiana, New Orleans, like sort of Seattle, big cities, or those regions around big cities will always be. But if you go to the Midwest, they're not going to visit every state every 2 years. They're going to kind of move around, but they're going to randomly select schools as they go through. So this is a great strategy in order to reduce the cost of data collection. All right. Kind of already talked about experiments, but this at least defines it more formally. We're going to talk about correlation, a little bit more in a few weeks. We'll define it statistically and visually. So, things can be related. And if you want to have a good time, there's a great website, Spurious Correlations. If you want to go see some fun ones to see why correlation doesn't mean causation. So here we have the popularity of first name Violet correlates well with Aquarial Guinea. Google searches for how much wood could a woodchuck chuck correlates with kerosene use in Venezuela, right? There's all sorts of fun ones. The one I always talk about, there is actually a correlation between ice cream sales and crime in New York City. Does ice cream sales cause crime, or does crime cause ice cream sales? Probably not. I don't think so. Right. So in order to have causals, it's really about that control. So going back to a question I see in the chat, how is cluster different from stratified? So good question. So in stratified, we're randomly selecting from all the strata. Okay. With clustering, we're first randomizing at the cluster level, then randomizing within the cluster, right? So if you care about a variable, right, and you want to make sure it's represented, you would not use clustering sample. The example I gave, like clustering is often done in ways to make it more feasible to collect the data. So the red lines means selected, or were randomly selected in these figures. Okay. So if you want to do an experimental design, there's sort of 4 major principles, right? First, control, right? You should be controlling what happens. Okay. Second, you're going to do some randomization, right? You're going to flip a coin to decide which group someone's going to go in, or a dice. It doesn't have to be 2 groups. You can have 2 treatments and a control, or whatever. There's a lot of different combinations. Replication, although this is not often done. In the social sciences, you Google the replication crisis. There are a lot of psychological studies that people have tried to replicate and they don't get the same results. Right. So, doing one sample is often insufficient to provide evidence. You need to do it over and over. And then fourth, blocking. So blocking is like the cluster random. It's sort of the analogy here, right? So if I want representation here, the example I gave is I'm going to stratify an ethnicity. So I make sure all ethnic groups are represented in my sample, right? If you're talking about causality, what I'm going to do is block on something and then randomize to treatment control within the block. And that ensures I have balance across that, whatever that variable of interest might be. Okay. Some other things you need to be aware of: placebo, that's usually a fake treatment. If you end up doing medical research or epidemiology or things like that, drug trials often use placebos. That's sort of a fake treatment, right? Very common in medical. oftentimes, you give a sugar pill. So somebody can't tell if they're in the treatment or not, right? They're still taking a pill. Placebo effect is, I think, one of those outstanding scientific questions and occurs a lot in sort of medical research where people who are assigned to the control group still see positive outcomes. And we don't fully understand it. It's a phenomena that has happened over and over again. But that's what that means. So blinding is a case where the experimenter, so if you're talking about drug trials, the reason why you give a placebo is so that the person in the study doesn't know if they're in the treatment and control. Okay. So that's the blinding. Double blinding means, let's use medical again, the doctor and the patient don't know if they're in the treatment. Okay. And that has become, double blind studies have become really important because there's a lot of evidence that doctors often have favorite patients or where they get patients in the treatments that violate the randomization procedure, which therefore violates the ability to make a causal claim. Okay. So that's why we do double blind studies. And this figure here is trying to summarize, these sort of two components to data collection all in one, right? So we could have random sampling or no random sampling. So if we have random sampling and random assignment, right? So we can make good generalizability, right? So random sampling gives us good generalizability. No random sampling gives us really no generalizability. Random assignment gives us good causation and not gives us, good, correlation. So this is like the ideal situation. We randomly sampled and randomly assigned. That gives us good generalizability to a larger population. But this rarely happens. Okay. Usually what we have is we can do random assignment, but not sampling. So we get good causality, but the generalizability is suspect. Or we have good randomization or random selection, but no assignment. So we get good generalizability, but we can't really make causal experiments. So generally things are going to fall into either being observational studies or experiments. This, like I said, is the ideal. And then occasionally we don't have random sampling or control. And so those are just kind of more problematic observational studies. I want to say one more thing about causality. So, oh, you can. Zig, thank you with ice cream and crime. I hope you're not a sample of one that makes that correlation perfect. I'm not applying anything. I'm sorry. So in the textbook, right, it's going to say the randomized control trial is the gold standard. Now, as somebody who does research in estimating causality from observational studies, I want to take yes, it is true, it is the gold standard. But I also like to point out that the randomized control trial is actually already a compromise from what a true causal effect is. And thanks to the Marvel multiverse, I find explaining this a little bit easier. So what a real causal effect is if we have some research subject, right? I tend to work with students. You could be medical, you could be working with patients. I have a colleague who did genetic research and so worked mice all his career, right? Whatever it is. What I want to do is split the universe into two, right? Doctor Strange style, right? Where the only difference between these two universes is some condition that I am controlling, right? I have condition A and condition B. Everything else is the same, including time, because that could be a confounder, right? And so I allow, condition A happens in universe A, condition B happens in universe B. Everything else is literally the same. And at the exact same moment, I measure some outcome, right? One happened under condition A, one happened under condition B. So the true causal effect is taking that same research subject and measuring the difference when they're in universe A and when they're in universe B. Okay. That can never happen because we don't live in the Marvel multiverse, right? So what we do is we have a research subject and we flip a coin and send them down one of these universes. And what we're saying is if we do that enough or with enough research subjects, any difference, any other confounders in the universes that may influence that outcome will balance out, right? That's what the randomized control trial. So it is already a compromise. Let's look at it this way. What we have on the left is, imagine I have 30 individuals and I'm stipulating there is a true causal effect of 4.5, regardless of where that person starts, right? So if I look at this individual, if they get nothing, they are this blue dot. And if I give them the treatment, they would increase by 4.5. So the length of all these lines is 4.5. Why are they spread out? What I did here is I randomly generated a data set with a mean of 100 and a standard deviation of 15. I picked that so I can have a concrete example, right? It so happens IQ tests are designed to have a mean of 100 and a standard deviation of 15. So if you want to be concrete about this, I'm going to say I have some intervention that no matter who you are and no matter where you are on the IQ spectrum before you start, my intervention will increase your IQ by 4.5 points, right? That's what I'm saying, right? And that's on the left. So if I take the average between all the blue dots, and the red dots, that's going to be 4.5, right? The length of all these lines is 4.5, so the average of all of them is 4.5. So what do we do in a randomized control trial? In a randomized control trial, we actually only observe one of those 2 points. So for this individual up here, they were randomized to the treatment. So I keep their treatment observation. This person was randomized to the control group. So I measured their control outcome, right? All the way down. So on the right side, I just randomly picked one of the 2 observations from the left. And now what I do is I average all the blue dots, and I get this vertical line, and all the red dots, and I get this vertical red line. So in this particular randomized control trial, my effect is negative 5.3. Not only is it not 4.5, it's in the wrong direction. But what happens is if I can do this over and over again, right? And that's what this simulation is doing here. I'm going to randomly select from this 30 people 500 different ways of combining that randomization. I get this distribution of differences. And so the mean of that distribution is actually pretty close to 4.5, right? So on average, right, again, that goes to why that replication is really, really important, because some of those samples, some of those randomized control trials had negative effects and some had overstated the effects, right? But on average, if I could do it a lot of times, we're going to do that. We will come back to this concept in a few weeks, and because this also is a precursor to a phenomena that makes making statistical inference work. Keith, I'm sorry if this was hard to read. The slide will be up for you to look at, pretty shortly after the class. So if you want to dig in, but that's a good comment. I'll see if I can increase the contrast of this going forward. All right. So that concludes this is like the key concepts of what we want you to know from chapter 1. So I'm going to throw a link to the 1-minute paper. So please complete those, but we will stay on as long as necessary to answer any questions you have about, how we get data. So that next week, we're going to start talking about summarizing data. And so chapter 2 is actually going to be split into 2. Next week, we're going to talk about mostly summarizing data. And then the week after, we're going to focus on ggplot and data visualization, because I think that is a very critical skill and very important to have. So it's worth spending a little extra time on that. Questions?
Yeah,
what was the y-axis?
Oh, go ahead. Who was asking the y-axis? We'll do that one first.
That was sorry. Yeah, what was the y-axis on the left chart over there?
On this slide,
Yep.
these are each it's an individual. So this is
Okay.
person 1, 2, 3, 4, 5, 6. Up to I have 30. I'm sorry you can't see that. That's 30. The x-axis is this was randomly selected from a normal distribution with a mean 100 and a standard deviation of 15. If I don't know if I have it ready available, but I think the way I did this, I could actually show you if you're so interested. So if let me just create a new R script. So what I think I did, I can look at the source of the slide, but let me see if I can recreate it. Might be more interesting. So I could say x equals we'll talk about these functions, but there's a function called R norm, which is going to, if I do question mark R norm, it's going to randomly select from the normal distribution. You're going to see there's 4 different functions. We will talk about these in details when we get to the distributions chapter. But so what I can do is say random normal, I want 30 of them, and I want the mean to be 150 and the standard deviation to be 15. Again, because that's what IQs are. So if I just look at the histogram, right, I get that. But oops, I meant to do library, right? So I'm gonna have X, and then so I'm actually gonna create a data frame. I'm gonna say X. Actually, I'm gonna do it this way. I'm gonna say X is 1 to 30, Y, or I'm gonna say control is equal to X, and treat is equal to X plus, what did I say, 4.5, right? So now I have this data frame, right? So I have an ID. Under the control condition, this person got negative 0.8. This is 4.5 plus, right? So this is what I did. I could do ggplot now on data frame. I could say X equals X. No, I'm sorry. I say yeah, X equals X, Y equals oh no, I'm sorry. X equals control. Let's start here. And then Y equals X. And I could do geom point, right? So that's where I started. But actually what I want to do is say, instead of putting it here, I can do it this way. I'm going to say X equals control and color equals blue, I guess, right? And then I can add, I'm going to put it on a new line. I can then do a geom point, AES X equals treat, and color equals maroon. I'll do because it's a little bit darker, right? So each of these is 4.5. So that's really all I did. And then I could just say, DF assignment, let's say, is equal to sample. I'm going to sample from true and false, 1, and I want replace equals true. Actually, I take that back. I need 30, right? So now what I did is, I could say, okay, this person was assigned the treatment, so I'll use that value, right? And that's how I built up that plot. Anyways, show you a little bit of behind the scenes. This might be a good place. If you ever have questions about this, I didn't post this slide deck yet, but if you go into the GitHub repo, and you go into the slides folder, so here's like the one from last Thursday. All the slides are created using R Markdown, same kind of structures you're doing for the labs. So you can always come in here and look up any of the R, if I have R code, which look at. So here I used R code to build the schedule because I keep the schedule in a spreadsheet. So if you ever want to look at this, you can always go up here and look at the source code of how I build a slide deck. So for this slide, once I post it, you'll see how I built these figures because the R code will be in the source code. Sometimes I show the source code like I did here where it might be worth talking about. Other questions?
I tried to join
Uh,
the Slack team and I was unable to because it said I wasn't a part of the
Um,
channel.
try this link.
Okay. Thank you.
Yeah. So if you're having issue, this link should let you in regardless of your email address. Let me know if that works for you, Evelyn. If not, throw your email in the chat and I'll just send you an invite through Slack. Any other questions? All right. Well, then we can call it like 8 minutes early.
Jason,
Typically won't end early, but we can end early tonight. Yeah, Alexander?
Jason, I have a question. Yeah.
Sure.
It is okay if I switch gears and ask a question about Lab 1?
Absolutely.
Okay, so I'm getting an error using the knit-r. It's telling me that apparently in the beginning of the RMD file, there's an image file for an R interface graphic. And it's saying that that graphic is not found.
Okay.
I've tried Googling it every which way.
So
and
did
not
you
finding
use
any clear answer.
did you use the start lab function?
Yes.
Okay, so let me do this. So if I'm here, I'm going to do library data 606, and I'm going to do start lab 1. So it's complaining about this.
Yes.
Okay, so if I go into the lab 1 folder, do you see an IMG folder in that
Yeah.
PNG file?
It
You
is
do?
there, but it's not detecting it.
All right, so here's what because it's not critical, you can go look at the picture on its own. You can add so let me show you. There's a couple different ways we can do this, I think. Yeah, so if I click, I kind of know this. What I really want to do is say eval equals false. So if you add this, comma as an option, I put it in the chat for you. It won't try to run this R code, and that'll hopefully allow you to knit. You can get to it if you click this little gear and it says output. I could say don't run code, which it moved it over there. So I can change. So you can have different options. This way. You could say show warnings. You could turn warnings on or off, et
Can
cetera,
you
et
show
cetera.
how you brought that pop-up
There's
just now?
this little gear.
Oh, okay.
Right here. Yeah. So one of the things I
Got
like
it.
about RStudio is they try to give you visual cues to a lot of features. And so, but if you notice, I want you to pay attention over here, right? It's really changing options in this part right here. So over time, by the end of the semester, you're going to know which ones you want to use and add, right? Eval, the ones you're going to want is usually eval equals true or false. Echo equals true or false. So echo, if you have echo equals false, it will run the R code, but keep the output, right? When you're writing reports, I do that a lot, where I don't need my audience to see the code that generate the table or figure or the outcome. I just want them to see the outcome, right? And then there is this results. In this case, it's as is, and that's because it's getting an image. There are certain situations, like if you're creating tables, but I don't want to overwhelm you yet. So over time, really the best way to, if the way I always learned this stuff is I saw what people were doing, and then I just went and looked at their source code and copied and pasted it, or try to, what option did you put to do that? But you also have Angela and I to ask. It's like, I can't get this to work. What do I need to do to make it pretty?
Thank you.
So do that. So the other thing, I think I don't know if I talked about working directories. So the one challenge with the way we set up these labs is that when you click knit, okay, it is in essence running relative to where the RMD file is, right? So this, okay, it's trying to open a file. So this is it's looking for a folder image, which is right here, and the R interface. However, when I'm working interactively right now, right here in the console, this is my working directory, not where the RMD file, right? So if I try, if I say list.files, I think this is how I showed it before, right? This is going to list the files here, right? So I have archetypes.r, right? This folder. But if I go to lab 1, for example, a couple things I could do is there's a function called setwd, or in RStudio, I can go more, set as working directory, right? And now if I call list files, I'm getting the contents of this folder. So when I'm running stuff interactively, for images doesn't make a whole lot of sense, but like when I'm trying to load data files, like there's some data files in here, and I'm running interactively, it's usually going to, you assume this is where I'm working from, not where the RMD file is, unless I make them the same. Okay. So when so it's just about the alternative is I would have to use an absolute path and have to say, you can see my absolute path there. I have / Dropbox, personal project, blah, blah, et cetera, right? But sometimes I usually just want to work relative to wherever I am.
I tried that actually. I put in the full path and it still didn't detect it. It's really weird.
That is very weird. Can you send me a screenshot of the error?
Yeah, I mean, I have can I just send you a text in the message box?
Yeah, go for it. And then while you're
Okay.
sending that, I'll, Evelyn, I saw hand goes up, and then, is it Simon? I said Simon, right?
Semyon, but
Semyon,
I think
I'm sorry.
Evelyn had her hand up first.
Okay, yeah, go ahead, Evelyn, sorry.
I had the same problem as Alexander, and I just deleted that R chunk. Is that okay for this situation, or do you want me to?
Absolutely. Yeah, for this
Okay.
one, that doesn't matter that much.
Thank you.
So package. Oh. Okay. I assume you did the tidy text. Okay, I need to,
Yes.
I'm going to capture this error. I'm going to put it here for right now. Error with lab 1 with the RStudio screen. Okay. So that looks like a LaTeX error. Like it's looking for a particular add-on package that it's not getting for you. So I'm going to have to do some Googling to figure out why that's not coming in. Are you on Windows or Mac or Linux?
The Mac.
Mac. Evelyn, are you also on Mac? Okay. That makes it a little bit easier because that's all I have in my office. Although I do have an Ubuntu server somewhere. Okay, I'm sorry. Who had a question? Simeon. Yeah, sorry. Simeon.
Quick question on, I think last week you mentioned you recommended like creating a project in RStudio for this class.
Yeah.
Could you quickly explain that? Because I've done scripts, but I'm not familiar with projects, and I guess
really it's just kind of for now it's really just a way of collecting things into a folder. Okay, so here I could switch over. Oh, that's last year, so these are pretty old. Here's what I'm going to do. Hold on 1 second. I'm actually going to switch to my local RStudio instead of the server. Okay, so here right now I'm on, so I have a project created for this class. And when I created it, so if I create a new project, oh, wow. Why is this taking so long? There we go. I often just go, pick an existing directory because I've already created a folder for it. If you didn't, you would have to go and say, create a new one. When you create, so you can create a new directory. Now, if you go this, you can just do a new project, which is just a random collection of whatever you want. And it's really just going to define it to a folder. As you get, if you do more in R, and if you want to use RStudio for Python, which you totally can, you could see there's a whole bunch of different types of projects you can create that will initialize it for you. So for me, right, so right now I have this project for, so it's set my working directory to the root, so you can kind of see where this is. And the reason why I do that is like now, oh, some of you did the bridge workshop, so I'm working on modifications. So I can just go, do that. And if I switch over to, I don't know why this is taking so long. Right. So now I opened up the bridge workshop so you can see, oh, here's the folder where it is. Here are all the files. And it opened the files that I had open last time. So I can just return to this. So this is the R code. The bridge tutorials was written in R and Shiny and stuff. So I'm making some tweaks on it. Anyways, so that's, for me, it's just a great way. So you can create one for this class. If you're taking 607, you're going to have two projects. You can just keep, flipping between. Does that help?
Yep, thank you.
You can also have more than one RStudio session. So I often have 2 or 3 open at the same time. If you have a good, computer, that works out well. Anything else? Oh, thanks, Angela, for the workflow. Yeah, that's a good chapter on the R for data science. Any other questions? All right. Well, if not, I'm going to stop the recording. Wish everybody a great week. And we'll see you next week.
Thank you.